I want to be the very best. 7.1 Growth and Decay. We're going to start this brand new chapter with exponential growth and exponential decay. Let's start by doing our basic graphing. Here we have a graph, y equals 2 times 3 to the x power. The new thing that you should be seeing is that the x is in the exponent, and so this is what the whole chapter is about. In Algebra 1, you were doing equations with x's in it. In Algebra 2, you had equations with x squared in it, x to the third power and x to the fourth power in it. But now the x is in the exponent spot, and so the whole chapter is going to be dedicated to solving x's in the exponent. But let's just see what the graph looks like. All right, we're going to go old school graphing and use a t-table. Pick some negative numbers. Always pick some negative numbers. Always pick 0. We want to know what happens at 0. And then pick some positive numbers. All right, those are the numbers you get to pick. Once you pick those, you're going to go ahead and plug them into our equation to get those. All right, so as you can see, the negative numbers are very, very small, and the positive numbers actually go very, very big. If we plot them, this is what the graph looks like. And you can kind of see that what we're talking about with exponential growth, it starts pretty calm, and then all of a sudden it just shoots up. And that's what we call exponential growth. Let's look at the parent function. Y equals a times b to the x. That's just the general equation of an exponential function. A is just a constant, the number in the front. B, we call that the base. And then, of course, x is the exponent. All right. Let's focus on the b's. If the b is greater than 1, so a number bigger than 1, then you're going to have an exponential growth. So 1.3, 1.7, 2, 4, all those numbers will give you an exponential growth. But if b is in between 0 and 1, so like a decimal, like 0.24 or 0.57. So a decimal or a fraction that's between 0 and 1, then you have an exponential decay, which means your graph is going to go down instead of up. All right, so let's do some examples from the homework. Determine whether each function represents an exponential growth or decay. All right, so we have this. Notice it has the a part, the b part, and the exponent. We are focused on the b part. Ooh. This part right here. We're focusing on this part. All right, notice it is in between 0 and 1, so we have a decay. And then the direction says find the y-intercept. If you remember from Algebra 1, the y-intercept is when the x is equal to 0. So if x is equal to 0, you have to remember from Algebra 2 now, anything to the 0 power, what is that? So anything to the 0 power is 1. And so this whole thing will be 1. And then the 7 that's in the front, multiplied by that 1, is just 7. So the y-intercept is 7. 0,7 if you want to be exact. Let's do another example. Here we have 3 over 2, which is the same thing as 1.5. That's obviously bigger than 1. So we have a growth. And then the y-intercept is 0.5. 4 for the same reason. Last example. This one just looks a little bit different because it doesn't have a part of it. So is it missing the a, is it missing the b, or is it missing the x? The exponent is there. So is that 5 the a or the b? Notice it's attached to the exponent, so that's the b. The a actually is 1. It's like an imaginary 1 in the very front. All right, so because it's 5, it's bigger than 1, we have growth, and then the y-intercept is 1 in the very front. Let's look at some growth and decay formulas. If you notice, they're both almost identical. The only difference is you have a plus sign in one and a minus sign in the other. You can want to guess which one stands for the growth and which one stands for the decay. The growth is a plus. The decay is the minus. Let's see what each of the parts stand for. This a of x, or in this case a of t, is just the total amount after the time. That little a stands for the initial amount. That r stands for the rate, but make sure the rate is in decimals. And then of course this t stands for time. And then everything stands for the same thing in the other equation except for the minus sign when we have decay. All right, let's use this formula to see how it works in real life. All right, so let's say that you invest, or maybe your parents invest $1,000 into a savings account. So when you were born, maybe they were like, all right, we're going to start a savings account for this kid. And they put in $1,000. The bank says they're going to give you 5% annual interest. How much will you have after 1 year? So this is how we're going to calculate it. Using the formula, the exponential growth formula. There's everything plugged in. The initial amount is the 1,000. The rate is 5%, but remember we had to change it to decimals, so 0.05. And then the time, 1 year. To calculate this, you have to remember PEMDAS. Please excuse my dear Aunt Sally. You first do parentheses first. So add the 1 with the 0.05. Then you do the exponent next. So raise it to the 1 power. And then the last thing you do is you multiply by 1,000. And so it turns out that after 1 full year, your bank now has $1,050. So basically, the bank has given you $50 for keeping your money in their institution. All right, now 5% is a lot. Most banks don't give that much money. That's a lot of money. Usually it's very small, like 1% or 0.5%. But for the sake of doing this problem, we're using 5%. Let's see what happens after 6 years when you start elementary school or kindergarten. All right, so there it is. We plugged in the original $1,000. The percent is still 5. Ooh, this is supposed to be raised to the 6th power. Not. So that was my typo. My bad. Oh, well, there it is. So we have, again, use PEMDAS. Add the 1 and the 0.05 first. Then do the exponent next. 1.05 raised to the 6th power first. And then the last thing you do is multiply by 1,000. $1,340.10. So by the time you start kindergarten, you've gotten that much money. Let's see what happens when you graduate high school. Go ahead, plug it into the formula, put in 18 years for the time and see what happens. $2,406.62 if you originally invest $1,000. All right, and so that's something fun to know. If your parents started a bank account for you when you were just being born, and then it just grows throughout the years. That's how money works. Again, the percentages are a little bit off because most banks don't give you 5%. That's a pretty high number. All right, the last thing we're going to do is go backwards. How long will it take to save $1,628.90? Well, we did 6 years. 6 years, it got you 1,340. 18 years got you $2,406. So how many years do you think it's going to take to get $1,628.90? Here's the setup. They give you the answer, so we put that in the A of X or A of T part. Everything else is the same. You still originally started with $1,000. The bank still gives you 5%. Now we're looking for T. And this is actually a sneak peek at the rest of the chapter. How do you solve equations where the variable you're solving for is in the exponent? All right? And so today we're going to do guess and check. You're going to plug in a whole bunch of years to see which one comes closest to $1,628.90. All right, but throughout the chapter, we're actually going to learn algebraically how to solve this one. So for today, the homework is going to ask you to guess. Keep guessing until you come to the close answer. And if you keep plugging in T, it turns out that if you plug in 10, it'll give you the right answer. So 10 years. All right. Go ahead and try the homework, and I'll see you tomorrow.